Every month, over 1.2 billion users operate simultaneously on LinkedIn. At any given moment, they interact with an inventory of 50 million active job postings, a dataset that shifts constantly. Tying all of this together are 270 billion relationship edges, connections linking members to companies, skills, schools, and each other. This dashboard tracks the strict service-level agreements engineers enforce to make a network of this size usable. Complex graph traversals must complete in under 50 milliseconds. Generating a personalized real-time newsfeed has a hard ceiling of 100 milliseconds. Matching a specific user to the ideal job requires the same sub-100 millisecond execution. Routing this combined load, millions of operations per second, into a standard monolithic database crashes the system. Surviving this volume requires breaking the infrastructure apart into highly specialized, isolated, distributed systems. Engineering at this scale requires a total redesign of how data is stored, routed, and mathematically evaluated. Historically, LinkedIn managed its relationship tracking using a legacy system known as Gaia, which relied on disk-backed storage. Standard backend engineering principles dictate that if disk queries are too slow, you place a cache in front of the database. Exploring second and third degree connections exponentially multiplies intersecting nodes. Caching this tangled web of join paths is mathematically prohibitive. Engineers removed the cache, deploying Liquid, a normalized database using vertices and edges tables to keep all 270 billion edges in physical memory. To navigate this, Liquid replaces standard SQL with a declarative data log engine, allowing developers to map complex multi-hop paths without nested joins. When a user queries their network, the engine executes a breadth-first search algorithm. To prevent infinite loops within highly connected clusters, the system maintains a thread-local bit-vector visited set, marking each node the moment it is evaluated. And because it uses memory-mapped triple indices, resolving adjacent neighbors happens in constant time. By stripping away the cache layer and executing purely through distributed RAM lookups, query latency stays below 50 milliseconds, while throughput scales to 18,000 queries per second. While the graph handles connections, assembling a timeline of posts directly from that main database for every user is an impossible bottleneck. A professional newsfeed relies on a specialized 5-layer tashing architecture, entirely decoupled from the main graph. Distributing a post to 300 followers is manageable, but pushing a celebrity's post to 5 million followers creates a catastrophic write bottleneck. To solve this, the system uses a push model for standard users, instantly writing the post directly into their followers' local newsfeed caches. This guarantees an O of 1 read latency. When those followers open the app, their feed structure is already assembled. For massive followings, the system switches to a pull model. The celebrity's post bypasses follower caches entirely, routing to a dedicated table. When followers open their app, the service pulls their standard cached feed, queries the celebrity table, and zips the two payloads together at read time. Bifurcating the distribution logic based on follower counts protects the caching clusters from write-heavy crashes while ensuring every user sees an instantaneous feed. The hardest requirement remains: evaluating 50 million active jobs against a user's profile to generate recommendations takes too long for real-time compute. The architecture deploys an asymmetric computational funnel, trading speed for intelligence at each descending layer. Stage 1 is L0 retrieval, powered by a semantic understanding framework called Jude. In this two-tower neural network, unstructured user text enters the user tower on the left, while raw job descriptions enter the job tower on the right. Both towers independently convert this text into dense numerical arrays, mapping them as vector coordinates onto a shared mathematical space. Comparing the user's vector to every single job vector is impossible. The system uses approximate nearest neighbor search algorithms like HNSW. Instead of an exhaustive search, the algorithm draws a boundary around the user's vector, capturing only the job vectors physically located within that specific cluster. This fast mathematical sieve reduces the pool from 50 million jobs down to 5,000 highly relevant candidates in milliseconds. With the candidate pool drastically reduced, the pipeline routes the data into stages 2 and 3, a heavy ranking engine called LiRank. LiRank utilizes deep, multitask learning models, specifically residual deep and cross networks. Instead of optimizing for a single metric like click-through rate, which favors clickbait, LiRank predicts multiple outcomes simultaneously: the probability of a click, an actual application, and total dwell time. True machine learning scale means using fast algorithmic seeds to locate the correct mathematical neighborhood, then applying computationally heavy models to find the exact house. The graph, the feed, and the recommendation pipeline all integrate together into a single continuous asynchronous loop. Consider a passive user behavior, dwell time, lingering on a post or a job listing without actually clicking it. That passive signal is instantly captured and streamed through Kafka message queues. This diagram tracks that event flowing from the feed into Kafka and directly into Apache Pinot, a distributed OLAP engine designed for high concurrency analytical aggregations. Pinot is strictly isolated on separate clusters from the Liquid Graph database, ensuring these heavy analytics never impact traversal latency. Pinot immediately processes this behavioral data and routes it straight back into the Jude user tower. Within 300 milliseconds of that single linger, the system recalculates and updates the user's active vector embedding. Because the user's coordinates in the vector space have shifted, the very next job retrieval or feed poll they request will yield adapted results. Building a network for 1 billion users requires strict data isolation, in-memory topologies, and real-time feedback loops that make the platform adapt with every interaction.